I didn't receive any specific questions, but I'd like to go through some more examples, and I think I will be posting a practice assignment. I thought I had one with some questions about reductions, oxidations, some of this carbonyl stuff, so you can practice with that. If you are looking for more problems to do with it, they are in Chapter 7. We are basically working through Chapter 7 of Ogilvy. And so you can find a lot of the content and practice questions in there. So hopefully that works. As always, like I can talk about some stuff, but I'm also happy to address any questions because that's what this is really for. Otherwise, I'll create some problems. Okay, so last class we discussed oxidations and reductions, and I said we're going to get back to the mechanism of oxidations later. Today I want to talk about some other simple additions to carbonyls. And so what we're really relying on here, I don't know, that. So we can draw this a little bit neater maybe with a lone pair directly on there. And there's a negative charge on that. So this is an acetylide. And that's because that is acetylene. That's the triple bond. So some brilliant person thought that we'll call a negatively charged sp carbon that is making a triple bond an acetylide. And so that's what I'll be using. Sorry. So these can react directly, unsurprisingly, the same way as everything that we've seen so far reacts. Okay, now I'm going to answer something I've kind of avoided going through. And that's that under these conditions, that is what we have. So if you, when you do the reaction, what we would normally, and we're going to break this all down, is we would make this thing first. So we'd be preparing our reagent. We would then do our main reaction, which is this, and then we need to do a workup. And your workup normally involves adding water. Those of you who are doing the in-person labs, have you guys gotten to extractions yet? I'm watching the chat. Great. So extractions are basically used for workups. So you run your reaction. Excuse me, I'm dying of COVID apparently. And then that wasn't funny. I'm very sorry. That was inappropriate. And then what you do is you add water. And normally the water is doing a bunch of things. So in the extractions, we're talking about a lot about how, okay, the organic stuff goes in the organic phase, salts and stuff goes into the aqueous. We're using it to separate. That's true. We're also using it to neutralize and just solve charge problems. So normally you would work this up with dilute acid. What does that mean? It might be 0.1 molar hydrogen chloride, might be 1 molar hydrogen chloride, whatever. Might be saturated ammonium chloride. There's a lot of different dilute acids we can use. It could even just be water, but normally we want a little bit of acid. And that's often just shown, and I'm just going to use this simplification, acid in water. I'm not saying if it's HCl, I'm not saying if it's nitric acid. It wouldn't be nitric acid. It might be HCl, it might be sulfuric acid, it might be trifluoroacetic acid, it might be ammonium chloride. There are lots of different things it can be. It doesn't really matter what they are. They're all just sources of H+. And our negative charge that we generate from a reaction is going to react with the H plus to give us our product. So in general, very few exceptions, products should be neutral. You shouldn't leave some negatively charged oxygens or positively charged carbons lying around and say, hey, I've got my product. Your product should be neutral. So let's take this reaction and figure out what's happening, because what I really want to talk about, all I had on today was answer any questions that there were. Oh, you sent a question, my good to us. If you sent it really recently, that might be why I didn't do it. Oh God, there are so many emails. Yep. Yeah, we can work through that one. And it's actually a good example. So we have what we then have is we have these different components of the reaction. So most reactions are normally set up of like 3 different steps. We might not see all these steps, but preparation, reaction, workup. I'm having trouble with lecture 17 and 18. What would you recommend I do if I'm in that situation? I'm going to ask you a really stupid question. What are lectures 17 and 18? They're the stuff on this, right? It seems you're not alone. Okay. What I would do is I'd be reading. First of all, I'd start maybe reading chapter 7 of the text. I think one of the challenges with lecture 17 and 18 is they are lecture 17 and 18. We kind of skipped some other ones. So the way I've delivered those, I assumed some other content, and we hadn't gotten to that content yet here. We're going to land all there at the end anyways for the exam. But you point out a hole, which is I probably need to re-record those in the future to make sure it flows if I keep this flow. Yeah. What I would think is, so maybe at this point, we're going to be seeing a lot of different stuff. Yeah. So these are lectures 17 and 18, I believe, at this point here. Let me just double check this. Sorry, I'm gonna. Yeah, so I think in some cases it assumes some knowledge on some things. Okay, so we're gonna be going over all this stuff. Yeah, so let's go over this stuff. So that's why I want to walk through some of these examples a lot more. So and I promise we'll do some proton transfers. So we have these 3 different. Let's finish this, and then I'll tackle Guntas's question, and I'm going to try and tackle some of these issues that we're seeing with them getting in the chat here from Carolyn and stuff. So we have these 3 steps for every reaction. The preparation here was hidden. We had to make this reagent. And I'm going to show you how we did that. This was the main reaction. This was the workup, and the point of the workup is to make things neutral. The point of the preparation is often to make things reactive. So this overall reaction that I just drew there would actually be so here we kind of have it all working out there. So the first step, I'm trying to make something reactive. The second step, I've got my main reaction. The third step, I've got my workup. Often, I'm not going, when I'm asking questions, I won't give those conditions to the workup. You just assume acid or base workup as you need. We'll talk about what that is, and that's all about the proton transfers. The first step, the other two will always be given to you when relevant. And so what we need to do when we see something like this is normally the first step of every reaction involves something that's really, really reactive. It might be an H+, it might be a really strong base, it might be a Lewis acid. There's going to be something that's really reactive. In this case, it's sodium hydride. That's basically an H-. It's a really strong base. It's okay to be a bit lost too. This stuff is really hard. So the first step is that. Now, why are we taking off that hydrogen? Because this carbon here is sp hybridized. Those electrons are going to be in an sp orbital. This is pretty stable. As far as carbons go, it's about as good as you can get. Good luck removing a proton from carbon under almost any other situations. We'll see examples where we do it. But there's no resonance. There's nothing we can stabilize that with. You can't do resonance without electrons. But they're really, really stable charge. And so this is something special about acetylides. Acetylides are very, very stable. We then use that to attack carbonyl. So this is step 2. This is step 1. Yeah, this is coming from NaH. Because it's Na plus H minus, right? You can kind of, whenever you see sodium or potassium or lithium, you can mentally dissociate them. H is taking the H. We're generating hydrogen gas. Then we have the lone pair on the acetylide attacking the carbonyl. We just saw this. This is the same pattern that we've seen. And then we have step 3, which is the workup. Yeah, that's exactly it, Alan. Sorry, it does look like OH. I'm really sorry. That does look like OH. It's not H minus. Hopefully that's better. Sorry, Alyssa, that's a very good point. The H2 here is coming from H minus reacting with H. The product of the reaction if we're trying to balance our equation. We don't need to balance our equation, but if we're trying to keep track of that, then we're generating hydrogen gas from hydride attacking hydrogen. Yeah, just if you're wondering where that's going. So this kind of illustrates these three steps that we're looking at. Now, what I'm going to take a look at is the question that Gunther sent me. So treating a nitrile with excess lithium aluminum hydride. Now the answer is acid and water. Sorry, the answer is an amine. Now this reacts, we saw lithium aluminum hydride react with a carbonyl, and we saw what happened you see movement out of the corner of my eye, but it's just my screen updating. And so with a carbonyl, what we did was lithium aluminum hydride reduced the carbon oxygen double bond to a carbon oxygen single bond by adding an H minus. And we're going to see the same thing happening here because we have the same principled problem. So if we think about this and we think about the resonance structure, this is one way to do it. You don't need to draw a resonance structure. But you have kind of the same kind of idea of a resonance structure with the nitrile as you have with the carbonyl. The negative charge prefers to be on a nitrogen. The carbon is positive. So if we're using lithium aluminum hydride, which is this H minus that is not basic, generally, because it's attached to the aluminum, so it's kind of modulated. It's not fully basic. Mediated, I guess. Moderated. Moderated is the word I'm looking for. Then what we're going to have mechanistically is a negative aluminum. I'll draw a capital non-cursive A. And I might draw my L as cursive. Negative aluminum with 4 hydrogens on it. One of those hydrogens is going to be delivered to the carbon, which will break part of the double bond to release an N minus. Now, we can't immediately add another H minus to that because we get an N2 minus, and N2 minus is just weird. But we can remember that we have some lithium floating around nearby. So let's do that. You could also attack the aluminum. That would also be okay. But let's just do this with lithium. So this, yes, this reaction is asking, it's a good question, Megan. It's asking, what is the product of reaction? Product and mechanism. You know what, if I'm asking for the mechanism, I should probably do the right one. It's going to be aluminum, it's not going to be lithium. It's just more right. I'd accept the other one, that'd be fine. It's just, this is more right. And the only reason I know it's more right is because I know that somebody has seen this. So now we actually have an interesting situation, which I am going to promptly ignore because let's get to that complexity in a moment. I'm going to put a little star here and say, ask me about this later. If any of you care in this in 3 weeks. But we can just do the kind of quick and dirty version of this. Which isn't wrong, it's just not completely right. So we've now added 2 equivalents of hydride from the aluminum, 2 different versions of the aluminum. Now I basically knocked this down as much as I can, so I'm going to add my acid and water. I'm going to start a new page because I'm going to give myself a little bit more space. Add a bit of acid. To none of our surprises, let's get rid of that N plus or N minus. I think what we can do then is we can think that this is now in equilibrium. With that, which is kind of a step back from, like, we added it in the first place, we can take it apart. And then if we add some H plus to that, we've neutralized the nitrogen. So the question here, there's a few things I want to point out which I really like with this example. One is, I was really careful not to generate a double negative on nitrogen at any one point. I do have something that looks really unstable here. It's because I'm lying to you a little bit. It's not that bad, but still it's really bad. It's also not quite true. This is going to lose a hydride very quickly and sort of become neutral aluminum, which will then allow the nitrogen to be negative a little bit more easily. But it's just a few more arrows. I'm trying to keep this simple. I'm lying to you. We'll come back to this a little bit later. I just don't want to overwhelm you with way too many arrows right now, which is why if you looked at lectures 13, 14, 15, 16, or whatever it is, and you're kind of lost still, I get it. Those were long lectures because we spent a lot of time on that material because it's pretty tough stuff. So we're going to be able to go through a lot of examples of that, which is why this is why I'm getting really excited about the whole flip class thing. I think that's what's going to be the absolute best. But what we ended up doing was trying to keep, at no point did I get 2- charge on nitrogen. And so I put my hydrogens on, and then I took my charges off one at a time on the nitrogen. So dealt with one negative, dealt with the second negative. Just making sure I never saw a 2-, never saw a 2+ on any of the normal sort of second row elements. Okay. Yeah. So excess aluminum hydride means use as much as you need to react everything to the end. So I could have said, 10 equivalents. You only needed 2, but I could have said 10. Excess just means excess. Like there's more than you're going to need. Keep going until you can't go any further. That's what excess means. Now I do want, let's talk about proton transfers. Why do we put negative charge on nitrogen twice? Why not once? Well, the problem is that we do it once here, so we put the negative charge on first. I could then add the other H immediately. But the problem is if I do that, then I'll have N2-. N2- just isn't going to form. You're never going to, I don't have my camera on, so you can't see me waving emphatically. You're never going to have N2-. So we need to kind of add the negative charges one after another, but we need 2 of them because we need to break the triple bond, because we need to break the double bond, then we need to break the double bond that forms after that. Jesse's question, where did the aluminum go? The honest answer is I don't give a fuck. We're always going to worry about, the truth of the matter is it turned into aluminum oxide, and we can talk about all those mechanisms later if you want. I'm perfectly happy doing that. Right now, I will terrify people. At this point, we don't need to matter what happens to aluminum. Right here, I've drawn that we have an equilibrium where we can break that nitrogen-aluminum bond, bring the electrons back onto nitrogen. We have aluminum floating away, and it just goes away. It gets dealt with in the workup. So Guntas, you can definitely have double bonds in products, but if you're treating a carbonyl with lithium aluminum hydride, or a strongly polarized bond between carbon and nitrogen, or carbon and oxygen, or carbon and sulfur, or carbon and phosphorus, and it's a multiple bond, lithium aluminum hydride will knock that down to being a single bond. How do I know it's in equilibrium? Everything's in equilibrium, basically. Because basically I put this on, this is kind of like an exact reverse of that. We put it on, we can take it off. Any metal attached to anything is always in equilibrium. That's a really long bond, right? Like aluminum nitrogen is not a fully covalent bond. It's not fully ionic. It's kind of in the middle there, and squishy middle, but it's a long bond. So we can think of it as being attached and then occasionally being broken and snapping back in and being attached again. I can conveniently think of it being broken so I can get that negative charge to react with an H+. So I think this is mechanistically, this is a very tough question. On the theory, up here, the top right, on what happens, it's very similar to what we see with esters. Actually identical to what we see with esters. It's just we have that extra negative charge in here. With the esters, we deal with it by losing an oxygen. But essentially, lithium aluminum hydride reduces things down to single bonds, like carbon heteroatom bonds down to single bonds. Yeah, this is a reduction. Alyssa, this is precise. That is exactly it. It's a reduction. We are adding bonds to hydrogen. Do nitriles always want to be amines? I've never thought of that question. It's a good question. Nitriles are pretty stable, but if you hit them with a lithium aluminum hydride, they want to be an amine, because lithium aluminum hydride does not want to be lithium aluminum hydride. So the driving force here isn't so much that nitrile is unstable, it's that lithium aluminum hydride is unstable and wants to give up H-. And the only person who can take the H- is the nitrile. But yeah, I'd imagine the amine is more stable than the nitrile. It's good. good question. I do want to talk about another example here where we can discuss getting a little bit ahead of ourselves into the next lecture. And that's discussing some proton transfer things. Can you go over this? So what the fuck is a proton transfer? Okay, so in the next lecture, well, you might have already watched it. Well, you might have seen an example like this. So I'm going to give the answer, and the question would then be provide a mechanism. So this thing is called an acetal. Or properly a ketal, because an acetal is when you have an aldehyde that is now making 2 bonds to oxygen. They're both like 2 ethers. When an aldehyde becomes 2 ethers, that is what an acetal is. A ketal is when a ketone becomes 2 ethers. This is a ketone. Nobody uses the term ketal, they just use acetal, but acetal comes from aldehyde. It just is. So what's happening here is relying on the fact that we're doing this in methanol. And this is all about Le Chatelier's principle. And remembering what Le Chatelier's principle states, it's that things go down concentration gradients. So if there's a freaking ton of methanol, this becomes favorable. We're going to then do the inverse, where we add a freaking ton of water and we go backwards under exactly the same conditions. But let's just look at this mechanistically. So again, we're thinking about the steps of how we think about a mechanism. The first thing we need to do is make something reactive. So if I look at what I have here, what's reactive? Can we break up methanol? We can break up MEO and H+, but let's just say we have H+ in there. So we add a, yeah, exactly. So let's just say a little bit of HCl. I probably should have just done this. A little bit of HCl. But in your mind, you see HCl, you just think H+. Sweet, great, you picked up, great, that's exactly it. So generally when you have H+, it's a hydrogen atom. It's not a hydrogen atom, it's a hydrogen ion. It's essentially a proton, because hydrogen is just a proton and an electron. And so we call it protonating things. So a proton transfer is moving a hydrogen around, and hydrogen is a proton. So we call this often like adding H+ is adding a proton. So we're going to protonate something, and we almost always want to protonate a lone pair. Not always, but normally that's the most reactive thing. And we have a nice pair of juicy lone pairs on this oxygen. So let's do that. And now what we've done is we've made our acetone, and that's what that is, 2-propanone reactive. We've made it charged. Now we can do stuff with it. Otherwise, it's just going to stare at things. Okay. So what we've been doing so far is using nucleophiles to attack the electrophile of a carbonyl. So take a second and draw the arrows from the nucleophiles attacking the electrophile of the carbonyl. Aha! Alan, we can try that and we can discuss that in a second. I'll come back to your question. It's a very good question, and I'm really glad you asked it. So Alan asked, how will we know not to have the chlorine lone pair attack the carbon? 2 reasons. One is I'm going to say that we have catalytic HCl. So again, I'm changing the rules on you and moving to posts. So we're going to have a little bit of HCl. The second reason, we're going to see why that's not going to do anything useful. But let's start with the methanol. And then draw your product you get for an immediate step, including all your charges. Because we don't have MEO minus. So Melissa, that's a good idea. Why can't we have that? We could maybe. So the aluminum hydride, the AlH4 minus is very, very unstable and highly reactive. Methanol itself doesn't want to spontaneously dissociate into MEO minus and H plus. Like that's just going to recombine immediately. The other big trick here is under acidic conditions. We have H plus present. And when you have acid, you can't have base. And if we had MEO minus, we would have base. But we can't have base because we have acid. And the reason you can't have acid and base coexisting is because they react together. So you're either you have an excess of H plus or you have a deficiency of H plus. And here we have an excess of H plus because we added some HCl. Yeah, so methanol attaches to the electrophilic carbon. So if you guys have had a chance amongst all the blah blah I've been doing to draw some arrows, hopefully you've drawn this. Now this is no different than anything we've seen. It's an oxygen this time. Who gives a shit? Okay. Now, what do you think is the most likely thing to happen instantaneously if I have that product? Like first, so I guess my first question is this stable? Yeah, good point. No, it isn't. Okay, so we got a couple of comments. Noor has the H gets dropped off. Madeline has will reverse. Madeline, you're a genius. Seriously, this is really hard to see, and you've got it. The most likely thing to happen right now is for that to reverse. Go right back to where we were. Damn things under equilibrium. That's not useful. It is the most likely thing to happen. But just because it's the most likely thing to happen doesn't mean it's the only thing that can happen. Because if it reverses, it can go forward and backward and forward and backward and forward and backward and forward and backward until something else happens, which Noor said is the H gets dropped off. So you're both right. Why is it not stable? It's charged. Amanda asked, why is it not stable? You got a charged oxygen. Oxygen doesn't want to be charged. You also have carbon making two single bonds to oxygen, and carbon really does not like doing that. Although that's what we're going to get as our product here. It's unhappy with that. So the most likely thing to happen is a reverse. The second most likely thing to happen is the hydrogen gets dropped off. But the thing is, hydrogens don't disappear into nothing. Like electrons have got to come from somewhere to take away that H plus. And so what we've got in solution is a whole metric ton of methanol. Note, I'm still drawing equilibrium arrows. Because all of this is reversible. Plus the methanol, and eventually I'll keep that in blue. Okay. Now, I call that thing up at the top there an acetal. I'm going to call this guy a hemiacetal because it's halfway there. It's like a Bon Jovi acetal. So we've got one ether and we have one alcohol. Alcohols are really, really, really unstable in a situation. Ethers are okay. That 2 bonds to oxygen, 2 single bonds to oxygen, it's okay-ish with ethers. It sucks with alcohols because the hydrogen can leave and it really wants to make a carbonyl. So what I want to do is I want to swap this alcohol with methanol another time. Now, right now, that molecule I've drawn, it's not perfectly stable. We got 2 bonds to oxygen, but it's okay-ish. We want to make it unstable again. So how can I make that unstable again? So while people are thinking about how we can make this unstable again, remove H. So add an H. Yes, Nora, we're going to add an H. Alyssa, if we're under base conditions, you'd be actually right. We would remove an H, but we're under acid, so we can't remove H's. We need to add H's because we've got too many H's. If we had a shortage of H's, removing H would be good, but we have an excess of H's, so we add H's. So we can add it to either one of the oxygens because we add it to any of the lone pairs, but if we add it to the bottom oxygen, we're right back to where we were. Is that likely to happen? Oh yeah, it's likely to happen, but everything's in equilibrium, right? It's not useful, we just go backwards. So let's try adding it to the other spot. So if we do that, we get that. Okay. So what we have essentially done is between, I'm gonna start a new page in a moment because I don't want to get this too crowded. But what we've essentially done is we've done a proton transfer here. Using the term proton transfer. Also can be written as plus minus H plus. So we removed an H plus, we add an H plus. We essentially moved an H plus around from one oxygen to the other. Yeah, I can draw the other one. Yeah, I'm less interested in it. You're absolutely right, but it's gone back to being methanol. How do we know we had to do that last step? You weren't done because I told you what the product was, Madison. So you had to figure out how to move forward. You're not there yet. It's also hemiacetals are not stable. Hemiacetals are either going to go back to a ketone or forward to an acetal, with one exception, which we will talk about this class, next class, sometime in the next little bit. So what we can't, so it's really tempting to draw and would be completely wrong is the purple arrows I've drawn here, which will take you directly to the blue structure. Right? So the one oxygen is just going to strip the H plus from the other. And that gets us to the blue structure we have there on the far right. I see this drawn all the time, often by professors. it's wrong? Anyone know why it's wrong and why my colleagues are idiots? Not my colleagues here, of course. They're all my colleagues at Windsor are geniuses. But it's a short form, and to be honest, I think everyone knows better. But that is not allowed, what I've just drawn there. The second methyl is still there. I just forgot about it. Glad somebody's paying attention. Should give like extra bonus marks or something to people who pick up errors on the slides as they go. You know what? Starting next class, you get like 0.2% extra on your final grade if you point out an error on my slides in the chat. Kind of like the way Jesse just did. 0.1%. Sam, I'll keep track. But anyone know why that's wrong? What about errors on a practice assignments? Sure, 0.1 for those two. I can learn a lot from that. I fixed a lot of them actually last year. It's amazing how many years I went through with some of those errors propagating and nobody noticed, which really makes me wonder if anyone did them. But yeah, if you find them, yeah, bonus marks. Anyways, I'll make lots of mistakes in the lecture. So, is it wrong because you're not doing intermolecular bonding? Close. So remember we were talking about ring strain. We go back to our lectures about conformation and ring strain. For the oxygen to make a bond with a hydrogen, it's going to almost need to be making a single bond. So what's the size of your ring going to be? Because the oxygen kind of does a reach around and grabs the hydrogen. Less than 5. Yeah, 4. There. 3. Oh, we're not good at counting, are we? So 1, 2, 3, 4 atoms. And 4-atom rings are very hard to make. They're very slow. You don't make 4-atom rings very easily. They're unstable. If this could be 5 or 6, sure, that arrow would actually be the way it went. But for 4, it's not. And it's almost always 4 because it's almost always this exact situation we've drawn here. It's almost always something attacked a carbonyl. You've now liberated carbonyl, and everything is 4 atoms apart. Like that's just the way this generally goes. And it can't do intramolecular with 4 atoms. So instead, we have to recruit methanol to kind of, walk over here, grab the proton, and walk over here and give the proton. So methanol is kind of shuttling the proton. It's still all about 4 or 5. Like build a model kit, and here I don't have enough carbons in front of me, but what I need is for these two to make a single bond together. And even when they're close like this, which is as close as they can be, that's still really far away, right? The bond angles are just bad. It can't reach. You have to put so much tension to bring them within single bond range. They're just not, and normally they're spinning around. So 4 is just not going to happen. It doesn't. And we know that because we've actually done experiments where, somebody actually wanted to try and sort of show, hey, can it be done in some cases? And you do that using deuterium labeling and stuff. And no, you can't. So, but we're not done. How did you know what to do at each step? This will get easier for you. How do I know it? Because I'm looking at what is stable and how to move forward things. So I think initially let's finish this off and then let's go back and try and see if I can give you an answer to that question, Melissa. It's a hard question. And this is why practice drawing stuff. Yeah, it's the same example. We're just continuing. Yeah, it was methanol was under the arrow, which means it's solvent. So there is metric fuck tons of methanol. There's probably like 1,000-fold excess of methanol compared to acetone. There is so much methanol. I don't know how to finish that sentence. There's so much methanol. I'll remove the comma and add a period. So at this point, what we can do is get you to go, what just happened? Which is the proper response. So I've used a lone pair on oxygen to regenerate a carbonyl. So this step here is the precise opposite of the first step. In the first step, we had a carbonyl, which was protonated and charged, and methanol attacked to generate this thing here, this hemiacetal. Now I have the hemiacetal, I've moved the proton around, and I'm regenerating the carbonyl, but the other way. So instead of having the carbonyl with the oxygen that has the hydrogen, we have the carbonyl with the oxygen that has the methyl group. And then the next step is the same as the first step. Why did I draw this with methanol and not use water? Besides that, water would just take us back to the last step. There's a better reason for why I drew this with methanol and not water. Like why this is methanol and not water. Nor with the absolutely technical answer of saying because I need it to make the product. Yep, I agree. But I really like Isait's answer. It's because you have excess of methanol. There's 1,000 times more methanol than water. So if I reach my hand randomly into the bag of molecules, I am going to grab a methanol. I'm not going to grab a water. Methanol is your solvent. There is so much methanol. The only water present is the stuff you've just gotten by releasing it. So you have this humongous excess of methanol. Methanol and water are very similar reaction-wise. They're both oxygens attached to two things and neutral. So all else being equal, there's just tons of methanol. And now we kind of have the workup stage. There's no clear workup drawn, but we can kind of do the workup with the methanol we have present. And so we need to make the damn thing neutral because it's not neutral. And to be honest, I should draw this as an equilibrium arrow as well. Instead of having that angled arrow, which really doesn't help any of us. So I'm going to use methanol to strip that final proton off. And I have this thing which looks a little bit like a guy lifting something, except he doesn't have a head. I have no idea what this looks like. Maybe an X-wing. So I've made my product. Now, let's try and think about Malitz's question, which is how do you know what to do in every step? Experience. which is great and easy for me to say. But let's talk about what we're trying to do. Is we're trying to make things more stable at every step, and we're also considering keeping our eye on a prize of the product and thinking about, are we getting more or less stable or staying about the same with every reaction? So in the first reaction, we have some H plus present. We protonate something, we protonate the carbonyl. We generate this species, this protonated acetone. There's a lot of methanol present. We can get rid of the positive charge on the oxygen by making the hemiacetal, where we have the OH and the protonated ether. Now, from here, the most obvious thing, as we pointed out, was just to go backwards, but that wasn't useful. So instead, we're going to go forwards. And the way to go forwards is we scoop up that extra proton and we make it neutral. So we deal with the charge. Notice that I'm always putting a charge on, or I'm dealing with the charge directly. I'm always interacting with the charge. I'm not ignoring the charge, because the charge is what drives reactivity, which is why we spent so much freaking time talking about what makes a stable charge. I can more or less trade, so we moved it onto the methanol, which is more or less a 1-for-1 trade. You know, we moved it from an oxygen to another oxygen. It's not a big difference. I can move it back to another oxygen. I do that. Now I need to deal with the charge. I can remove it, but then I just go backwards. Nothing happens. I know that I need to put a methanol in there. And we haven't discussed this a lot, but there's no way I'm going to break this carbon-oxygen bond between methanol. So I'm not going to be able to add a methanol to this oxygen by adding a methyl group. I'm going to need to add methanol as a unit. And since I have a water, I need to get rid of the water. And so the way I do that is I do the inverse of my first reaction. All reactions are technically reversible. Technically, everything is in equilibrium. Just practically a lot of stuff isn't. And then, so I do that. Now I have something that's very similar to my second structure, except instead of having a proton here, I have a methyl group. And now I can use methanol, and again, I am dealing with the charge. The way I deal with this charge, there's nothing to deprotonate here. The only way I can release this charge is by attacking the carbonyl and moving a lone pair from a double bond up onto the oxygen. I do that, and now I have a charge. I'm going to deal with that charge. I'm going to deal with it by stripping it away using solvent. And I know I need to do that because this is my product, and I told you it was a product, so that's what I'm going towards. Okay, what I'd like those of you who are eager to try something for next week, because we'll bring it up, is and what I'll do is I'll actually put in some values. I guess not next week, I guess Friday. Catalytic HCl, ethanol. So let's say there's one equivalent of this. Note that at all times I've regenerated my acid too. The acid was catalytic. I can say it's attached to the methanol, but I don't say that we got the H plus back. And we're going to come back to that chlorine question Alan asked next class because we're out of time this class. So catalytic HCl, so one equivalent of that, 0.1 equivalents of the HCl. So if I've got 1 mole of the guy on the left, I've got 0.1 mole of that, and 10,000 equivalents of ethanol. So what's the product and what's the mechanism? We're going to start next class by bringing this example up and start talking about that next class. Okay. So So I'm going to leave that here. Any immediate questions? Or I'm going to leave this to Samra to take over, and she can take it from here. What do you mean? What do I mean by equivalence? I mean number of moles. So if I have one equivalent of something, and I have 10 equivalents of something else, that means I have 10 times more moles of one thing than the other thing. And it doesn't matter if I'm talking about grams or tons or milligrams or nanograms or universes. I've got 10 times more of one thing than the other thing. Okay, so Samra's giving everyone a bio break. I'll leave the chat. So Samra, do you keep this channel open or do you start a new one?